Okay, let me. Okay, can you hear me? Start. Okay, so the question says that we have to find deflection of the beam okay, in order to do that, what we can do is, first of all, our strategy is that we will try to find the bending moment as we have discussed before. So let us go step by step. I will say AY plus BY equal to P. Then I will find the reactions at both the ends. So I will have minus AY multiply by L. Good morning, Roger. Good morning. Plus P into 3L by 4 equal to 0. Good to see you, Usman and Ghazal. AY equal to 3P by 4. So similarly, your BY will come out to be P minus 3P by 4, which is equal to P by 4, correct? Now the question says that you have to deflection of this beam. So what is your strategy? Well, your strategy is to cut this in two portions, right? How many students agree? The first cut will be somewhere here. So the first thing that you can do is you can put after you are cutting from left side. So I think students are telling me put a V here, put anti-clockwise M like this, define your X from here. So this complete chunk is your X, and yeah, just do it. So what you have to understand is that the bending moment before the cut, I mean before the P, and bending moment after the P will be different, right? I hope you remember that. So you cannot just straightforwardly do this problem. When you are trying to integrate, do you remember that integration that we were doing last time? I hope it rings bells. So when you were performing that integration, you had to utilize that bending moment, right? But now you will have bending moment before the P and bending moment even after the P. So for the two cuts. So let's call this as M1X. But before I do that, let me try to make one more comment that on this end, I also have a P that is acting. I apologize, AY, and AY I got as 3P over 4. And I think you do understand that X is from the left hand side. So no need to write it over and over again. X is defined from the left. And for me, this little element is X. Please focus here. The X is defined from the left side. Okay. Now that you understand everything, just tell me what is the moment. Everyone will tell me it will be minus 3P by 4 multiply by X plus capital M bracket X. Now, I'm not sure which books you had been studying statics, but you can always call it as M1, right? Why? Because you will have bending moment before the cut and after the cut. That's why I'm calling it as M1X equal to 0. If you don't want to use this, then you will have to specifically add a little comment here that this only works for X greater than equal to 0, less than equal to L by 4, right? You understand me, right? Okay. I hope you everyone is getting my point. Now that you have this, finish the question by saying, I mean this part of the question. is equal to 3p by 4x. Done? Now you will add the comment here. This is very important, that this only holds true for x greater than equal to 0, less than equal to L by 4. I'm not sure whether the equal to, yeah, okay, good. I think greater than equal to sentence is correct. Again, if a student wants to remove the one, he or she is allowed. Now repeat the same process, but this time you will make a bigger rectangle. This big. Are you getting my point? Now for this big rectangle, I mean beam, you will repeat the same process by saying, this is my AY, which is 3p by 4. And then you will say, this is my, I have to make sure that when I draw vertical, it's like completely vertical. Acha. This is downward. This is my V. This is anti-clockwise M, correct? And again, students who are saying, why don't you write M1 here? And why don't you write M2 here? So that's fine. Okay, and finish the question by saying that this time I also have a nice P that is sitting. So you will draw a nice P here. So this is your P. So finish the question. Let me use a color. So it will be minus 3p by 4 x plus m2 bracket x, then plus p into x minus L by 4, because students who are getting confused, this distance is L by 4, right? Do you agree with me? So I will say this distance is L by 4. Now finish the question by saying that my M2 bracket X is equal to, I don't know, just tell me the answer. 3px by 4. Yes.
What about the other empty space?
Huh?
Can we write?
1 minute. Sorry, say that again.
We said the left side is divided by 4. What about the right side?
So the right side is 3L by 4. The P is L by 4 from the left, 3L by 4 from the right. Actually, I did not understand your question. No worries, you can repeat the question. I will definitely answer.
Why we can't write this section?
Oh, you mean why can't we write 3L by 4?
Yeah.
Why are you writing x minus L by 4?
Yeah.
Good question. So let me answer his question. His question is, why aren't you writing 3L by 4? Why are you trying to write x minus L by 4? What you have to understand is that you are not finding the bending moment at a particular section. You are writing an equation of bending moment for x. Do you remember in your statics, your instructor used to ask you make a bending moment diagram. So many times you used to write these bending moment equation that has x on the right hand side, x, p, x, this x here. What was the purpose of all of those x? So you can find the variation of bending moment for each x. I want such kind of an expression. So now I will answer your question. I took this whole chunk and I put a cut here. When you put a cut here, what is the distance from this point to this cut? X, not L, X. That's why you do x minus L by 4. If you start doing 3L by 4, then you will find the bending moment where? You will find the bending moment at B. And what is the bending moment? at B? 0. The roller is not supporting any moment. So you will end up getting actually a 0. So you have to be careful that you want X everywhere. Positive. Okay, good. Good question, by the way. So we have 3P X by 4 minus Px plus PL by 4. Is there any mistake here? Can you just double check? Yes, no. Minus Px. I think there is no mistake. So M2 bracket X comes out to be minus.
Should be L by 4 minus.
Yeah, PL by 4. Like this. Ghazal agrees?
In the first equation,
Yeah, this one.
you wrote X minus L by 4. It's L by 4 minus X.
Really? Okay. I will answer. I will answer his question. Is equal to 0. Okay, Ghazal, your question is about this line, right? Okay, I will explain it. So you will have minus 3 by 4 multiplied by X. This X is the distance. This is clockwise plus anti-clockwise moment is M2X. Good. Then this about this section is plus P anti-clockwise into X minus L by 4. Are you getting my point?
Why are we taking the reference at V shearing force? Why are we taking the reference at V shearing force?
Where you want me to take the reference? I am making a cut here. So I am taking the moments about the section where I want to find the bending moment. If I want to find the bending moment here, I will try to find the moment about this section. So let me. This is X. Did I answer your question, or you want me to explain again? I'm making a cut here at this point, and I want to find the bending moment about this section. So I will take the moments about this section. Okay. Okay. Finish the question then. Is it clear? Yes. No. Is anyone confused? Don't hesitate. So now I have bending moment. This equation. Please remember, I forgot the equal to 0. So please make the correction. Of course, this is equal to 0. Then M2X is equal to 3Px by 4 minus Px plus PL by 4. And you get M2X equation here. I also have an M1X equation, this one. So now that you have M1X and M2X, let's go to the next slide. And why don't you all help me with M1 bracket X is equal to 3P by 4 X. And remember that X is greater than 0 and less than L by 4, agreed? And for the next one, you have X, what was that? Greater than L by 4, less than capital L. And I think we found the bending moment for this section as minus Px by 4 minus Px by 4 plus PL by 4. And it also answers Bahadur's question, right? That if you substitute X as L, what would you get? You would get a 0, which makes sense because the roller doesn't support any bending moment. If you substitute X equal to 0, you get M1X 0. That pin joint on the left also does not support any moment. But it also indicates that this equation, the left hand side, I mean this one, is only true between 0 to L by 4, and the right one is only true between L by 4 to L. So students who don't like this mistake, they can put an equal to. Again, I'm not very enthusiastic in getting worried about this, but you can add equal to. Greater than equal to, less than equal to. Now find the deflection result. You went through the steps of the last class, right? Do it. What were the steps? There was this formula, right? 4 or 5 formulas. What was the formula? EI d square V over dx square is equal to capital M bracket X.
Yes.
Good. You have a good memory. I'm impressed, by the way. Right, Ahmed? Ahmed Hassan Tawbash, right? Yes. So, okay, we will use this expression. And tell me whether you agree with me or not, Ahmed. EI d square V over dx square, where deflection is a function of x, is equal to 3p over 4x. Okay, Usman and everyone, I just want your attention on one thing. Now, if you want to put a 1 here, I don't have any issues. If you don't want to put a 1, that's fine. Putting 1 will always remind you that this part is only valid between 0 and L by 4. What you have to understand is that this beam is not as simple as you think. If I ask you how the deflection is happening, all of you will tell me it will happen like this. Follow me. Agreed? Now it will happen like this, correct? So there are 2 portions of the deflection. One deflection is between 0 to L by 4, certain polynomial. Another portion of the deflection is between L by 4 and 3L by 4. So if you want to put a 1 here, that's fine. And if you are not putting a 1, then definitely add a little comment. This is only true between 0 and L by 4. Anyways, similarly, you can continue with students who agree with me. EI d square V, again, you can add 2 if you want. If you don't want to put a 2, that's your call. Function of x is equal to m2x. And what is m2x? M2x is minus px by 4 plus pl by 4. Yes, Ahmed. Mehmet. Yes, Mehmet. Huh?
So that you won't get
I actually confuse Mehmet and Ahmed. Ahmed sits there, right?
No problem with your
Oh yeah, it's the same.
Yeah,
It's the same. Achha, yes.
Hocam, we try to find
The deflection.
Total deflection, right?
No,
For
we are
example-
we are trying to find the deflection at each point of the beam.
Like, for example, we bend it like this, and we try to find at this portion,
What is the deflection?
So we making it integration, right?
No. We are finding deflection at each point.
Each point, right?
What? So yeah, integration. Yeah. Integration. Sorry. We will do the integration. I'm sorry. I thought something else when you said integration. Yeah, I will be doing integration. Good. Because what is V? That is deflection. So just integrate 2 times. I think you understood. When you use the word integration, I actually thought about something else. That's why I said no. So integration, as you mentioned, I agree with you. So EI dV over dx is equal to 3p over 4 x square over 2 plus C1, right? Because we have 1 or 2 students who are quickly solving it themselves. I just want to clear one more thing before you end up making a mistake. When you integrate the left chunk, you can use the constants, let's say C1 and C2. Usman, And when you use the integration on the right hand side, you can use separate constants C3 and C4. So if you are using the integration constant C1 and C2 there, don't use C1 and C2 there. Does this point click you? Good. Okay, I did the right thing by stopping everyone. So now EI dV over dx is equal to minus px square over 8 plus plx over 4 plus, so C1 and C2 are for the left hand side, C3 and C4 are for the right hand side. So now E I dV, nahi, sorry, I think one more, sorry, V1 function of x is equal to 3p over 4 x power 3 over 6 plus C1x plus C2, and I will follow the same strategy there. EI, again, no one is telling us to use C1 and C2 here. You could have used C7 and C8 as long as you understand what you are doing, is equal to minus px3 over 24. I think it's the right time I start looking at my notes. PL x square over 8 plus C3 x plus C4. Agreed? Now, last but not least, I will have V1x is equal to, okay, this one is, you just tell me what are you getting? Px cube, 3 2s are 6 over 8. Okay, double check. Plus C1x over EI plus C2 over EI. Agreed. Now I will use a nice, beautiful orange color. So we will have V2 is equal to minus. Okay, I will ask a quick question to all four of you. Can I put x equal to 0 on this right hand side like V2? Can I put x equal to 0 in this part of the equation? No, right? Why? Because it holds true for, it only holds true for L by 4 to L. How can I put 0? Good answer. C3 x plus C4. This is clear to Hassan, right? That we cannot substitute x0 on the right, on this part of the equation, because this is only holding true for L by 4 to L. Yes, please.
We didn't put EI yet.
We did not? Okay,
For
sorry.
the second part.
Yeah. I think I missed. 24 E I okay, I think all of you understand. Very good. Now I will save my time. I will quickly go to the next slide, and because unfortunately or fortunately I have to write the equation one more time. You can just let it be like that, but I have to write on the next whiteboard. So please bear with me. Px cube over 8EI then plus C1x over EI plus C2 over EI, and similarly, bear with me please. V2 bracket x is equal to minus px cube. Okay, find the constants. Don't wait for me. Tell me what is your strategy. First, explain me your strategy, and then I really want you to do it. Take out a piece of paper, do it, because this will be nice exercise for you. PLX square over 8 EI plus C3x over EI plus C4 over.
I think we can the interval values. For example, in first equation, we will use 0 to L divided by 4. For second part, we will use L
Yeah.
divided by
What are the
4.
conditions? How can I find it?
X equal to F, V is 0.
Okay, hang on. Let's go step by step. You said
Yeah, absolutely.
V2 at L equal to 0 because of the boundary condition. What about this portion? V
V0 equals to 0.
at X equal to 0 is 0. Okay, then how many equations right now? One equation there, one there. I need one more equation for this side. Nahin.
Yes. Hocam,
Kitni?
burada X equals to L by 4 in this and this equation and then equation.
Good.
Yeah, and it's the V max, right?
Yeah, I think so. Good. I think it should be Vmax. But that is a secondary question, but your comment is just fantastic. So let me rephrase what he said. He said, you can also find V1 at L by 4 and equate it to V2 at L by 4, right? This is what you said, I suppose. That was nice, by the way. Hang on with me. How many equations right now? 1, 2, 3. Three conditions. This is a boundary condition. The V2 at L equal to 0. V1 at 0 is a boundary condition. V1 at L by 4 is equal to V2 at L by 4 because it's a continuous function. So at that junction, the deflection will be the same. This is what is known as a continuity equation. C-O-N-T-I-N-U-I-T-Y. Continuity. How many more equations do I need? I need four constants, right? C1,
Yeah.
C2, C3, C4. So how many equations more I need? One more, right? You are getting mathematically that I have 3 equations. I need one more to crack the 4th constant. You are pretty close, by the way. What you just told me, I will take it.
But in
So I will actually take Ghazal's comment and I will take it to another level. Look, you just told me that at this point, right at this point, the deflection given by the first equation and the second equation will be the same, right? What about the slope? You didn't think about it, right? The slope will be the same. Don't say 0 at this point.
why is it same?
Why shouldn't I? Because it's a continuous function.
Yeah.
Let's continuous function, the slope should be same. Achha, I don't want you to think that right now that slope will be 0 at this point. Look, I did tell you last time that the maximum deflection, we say that the slope is 0. That is correct. But in many complicated problems, you just cannot have a look and say at this point the maximum deflection happens or there. So you have to avoid using that as a condition on its own. Just go step by step. The dv1 over x dx at L by 4 is equal to that one. Comes out to be 0, good. Doesn't come out to be 0, that's fine. Okay, so do it and give me the answers, please. Okay, I think our students have given us. Yes, please.
How can we find E1 L divided by 4?
Yeah, I will tell you how. I will tell you how, but let me continue with this and then I will answer your question. So V1 at 0 is 0, 0 plus 0. In fact, I will answer Bahadur's question right now. Bahadur, this is, where is it? This is dv1 over dx, right? Take the EI on the right hand side and instead of x, put L by 4 and then come here, took the EI on the right hand side. Instead of x, wherever you see x, put L by 4. I hope I answered your question. Now, when you have C2 equal to 0, then you will go to the next and write V2 at L is equal to minus P. And then you will write L power 3 over 24 EI plus PL over 8 EI. Instead of X, we have decided L plus C3L over EI plus C4 over EI. Do you agree with me, right? Okay, anyways, now that you have got this, let's call this as, let's say 1. Let's call this as 2. Now we will take it to one more step and I will start saying, let's say V1 at L by 4 will be P L by 4 power 3 divided by 8 EI, agreed, plus C1 L by 4. Make sure that I'm not making a mistake, by the way. It's easy to make a mistake for me. Divided by, Hassan is with us, right? Everyone is with us. Okay. Plus C2 over EI. I'm not even sure why am I even bothering to write C2. Do you agree? There is no C2, right? C2 is 0. This is equal to V2 at L by 4. And what is that? Minus P L by 4 cube. So power 3 divided by 24 EI plus P L square over 4 square over 8 EI. Ghazal is with us, right? And so is Mehmet. Plus C3L by 4 over EI plus C4 over EI is equal to V2 at L by 4, correct? Okay. Then I will call this as equation 3. Now let's write the final equation. Is there a final equation? Yeah, the one Bahadur was asking, what about dv1 over x is equal to dv2x? So I think what I can do is I can squeeze it in here with a nice yellow color, okay? So we will follow Bahadur's strategy. Come here and start writing 3p over 4, 3p over 4, 3p over 4, 3p over 4, L by 4 square over 2, agreed? L by 4 square over 2, then go back, divided by EI, plus C1 over EI. Is it visible for our class? Okay, barely. Is equal to, now I will use a nice blue color. Go back, follow this. Minus P L by 4 square over A minus P L by 4 square over 8 EI. Then go back. Plus P L over 4, agreed, plus P L, I have one forgotten, huh? P L over 4, huh? P L by 4, L by 4, ठीक है. P L by 4, L by 4 EI. Then go back. plus C3 over EI. Okay, now this is my equation number. This is my equation number, how? 4. Ah.
But I think there's a problem at the blue equation
Why?
in second part.
Why? Let's go back.
Go back.
Minus P L by 4 square over 8 minus P L by 4 square over 8 EI
Yes.
plus P L by 4 L by 4 EI, P L by 4 L by 4 EI, EI in the denominator,
Okay. No problem.
plus C3 over EI, correct. Now you go back, go forward and write the final equation. V1x is equal to, you can find the constants yourself. I'm not doing it for you today. 4 equations and just figure out. You will get 1 over 8 x power 3. Agreed? Minus 7 over 128 L square x. V2 at x, I don't know. It's not in my notes. Now, if I want to ask you, give me the deflection at L by 2. Any student who can tell us how would we find? We will go back and we will say that we will have to use the V2. So you will say, this means you are talking about V2 at x equal to L by 4. Answer, I don't know, I haven't found it. Find the constants. Did you, by any chance, watch the last recording because you were not here? Are you sure?
But I understand right now.
This one you understand, but the last one was more difficult than this one because that was a distributed load. So go over it if you missed it. Okay. Clear?
In previous lesson,
There was a distributed load.
just distributed both, right?
But the same problem, but there was a distributed load. So, of course, bending moment diagram becomes a little complicated for students who have forgot the statics principles and everything. So you really need to do it by hand. Okay. Any questions for me today? So let's do another problem, but this time I will combine the 2 problems that I did last time. So let me save this. I just wish I could have shared this here somehow and just shown the slide. Anyways, let me just do it for you. So the problem is the one that we did last time. This is the problem that we did last time, if you remember. Agreed. We had this beam, and last time I went over. How many students agree? Okay, so we have, let's say, this is the problem that we did last time. So we have a roller. And this was, let's say, 20 kilonewton per meter. So you can look at your notes from the last time. We did talk about this distributed load, right? We talked about a real beam, and a real beam will have its own weight, and its own weight is distributed like this, right? You say that everything is concentrated at the center. That's just an assumption. Eventually, if there is even a wooden beam, that weight is distributed all over it. So an unloaded beam will actually look like this, right? Because its own weight is active. This is an unloaded beam that I created. So let's say this is and we have 150 kilonewton. 150 kilo. Now I have changed the problem. This is not last week's problem anymore. Now what I'm saying is, on this very real beam, 150 kilonewton is acting at a distance of 2 meters. Now what you have to understand is that this 150 is separate from the distributed load. So you are not going to, let's say, you're not going to say that this arrow is the distributed load magnitude and then something. No, 150 is completely separate. Distributed load is separate. The pink, then on top of that pink, I have a concentrated load of 150. That's why I used a different color. So this is 2 meters from here. Okay, and two meter, and this is 6 meters. So can anyone from their notes at least look at the solution that we created last time? 6 meters. If you don't have it, that's fine. Nothing to worry. Then this is okay, 6 meters. The question says that EI value is 100 mega Newton meter square. This is known as flexure rigidity. I don't think I ever used this term in front of you, did I? Flexure rigidity is the name of this EI. And if you're wondering, why are you giving us EI? Why didn't I give you E and I separately? Because EI is so much being used in these problems that just for your own convenience, I just gave you EI. Another thing is that the deflection is depending on what? EI. Why deflection is dependent on EI? Because if you have a beam that has a rectangular cross section sitting like this, and you're putting a load from the top, it will have a certain deflection, right? But if you change this rectangular beam from this to this, so you change it from here to like this, then the deflection will be less. Of course, we know it as a fact. Similarly, if you change the material from wood to some other material, for sure the deflection will change, right? So EI has an important importance. That's why your deflection has. Yes, please.
The I value is the cross-section areas I value, right?
No, I is the moment of inertia about the neutral axis.
About the neutral axis, yeah. Like the NZ Y.
Over I, that I.
Right?
That I, yeah, of course. So for example, this has a moment of inertia when the load is being applied from like this. It has a moment of inertia like this.
Okay.
About the neutral axis. And if it load is being applied like this, again it will bend like this, moment of inertia about the neutral axis. You know it, right? We have emphasized on this concept a lot. Now go back to your notes from the previous class. Can you at least double check if anyone has the notes from the previous class that I derived this? I derived this expression for So now in an exam setting, if this question appear, there are two ways of doing the question. Number one, you attempt the question as it is. How can you do it? Of course, you will make a cut right before this 2 meter. So you will have x greater than equal to 0, less than equal to 2. That is your V1. Then x greater than equal to 2. Exactly. X greater than equal to 2, less than 6. That is your 2. V2. So first find M1x, then find M2x, then find V1 bracket x, big expression, then find V2, big expression. Then you use the four conditions. At x equal to 0, I don't have any deflection. At x equal to L, I have 0 deflection. Then continuity equation that we discussed. Now, this problem will take a lot of time, but you have to do it. There is another way, and I don't want to call this other way as the easy way. I'm not even sure if it's the easy way. I'm just trying to tell you the concept. That other way is, but till now it's clear, right? Because I'm not going to do it for you. I think you have sufficient background in statics to do it. I have already covered a couple of examples now. You can actually divide this problem into two. Again, it's your choice. I'm not asking you to always do it. But no, I can ask you, particularly in an exam, to follow this strategy. But if I don't ask you, then it's entirely up to you. Yes, Usman.
What is W value? What's the distributed force?
I did not tell you, right? Oh, 20 kilonewton per meter. Good question. Sorry. Again, this is my mistake. 20 kilonewton per meter, because the beam manufacturer told me that because of the weight of the beam itself, it is 20 kilonewton per meter distributed over it. It is unloaded beam, and now I put 150 kilonewton on top of it. This is equal to this plus. Now all of the students are saying, what on earth is about to happen? I will put arrow like this. Then I will put arrow like this. Again, students are saying, what is happening? Then I will add then I will put arrow like this, and I'm coming to your desks. You tell me, how should I add them? I did not put the loads. Why don't you put the loads and tell me the strategy? Anyone? So I'm sure that you have figured it out. This will be the strategy, right? I will put a concentrated load like this. And then I will put the pink arrows. Agreed? Where? Boom. I'm sure that our students already knew this. So now technically what are you going to do is, you will follow the example that we covered last time. Get the Vx from there. And then you will add them together. So now technically you will have a deflection like this. By the way, deflection will not be maximum here. Ghazal, I think deflection will not be maximum here. I don't think so. You have to find the deflection. That's why I was telling you, don't do it. I think the deflection, maximum deflection might be a little to the right of it. So don't automatically think that the load is being here, there should be the maximum deflection. That will end up being a mistake. Probably, as I made the diagram, probably the maximum deflection is a little right to it. And then for this problem, yeah, now you are correct. The deflection will be maximum at the center. I actually agree with you now. So, in fact, I really want to go back, and in my notes, I don't want anyone to think that the maximum deflection will happen here, because one of the students actually thought this. So please spare my mistake. Okay. Whatever. I think you get the point. Okay, now do the problem yourself. Okay. Now go back to your notes and tell me what is the expression that we developed last time. Anyone? What was the expression from your notes? Last time we did this. So this one, Usman, the distributed load. Was it like this? You can double check. Minus W.
Hocam,
Yes.
I can tell you, hocam, if you want.
Please tell me.
It's WL x cubed
Okay.
divided by 12 EI.
Okay. Hang on. Hussein, was it like this? This is what I really want to double check. I will pull out the 24 EI and then you can just double check. Was it x power 4 like this?
Minus, yes.
Now I will give Hussein a few minutes to you to double check whether when I have pulled it out, does it look like the same or not?
Not really, hocam.
Oh, really? Well, that's
Yeah,
not
on my notes it says actually wait a minute.
because 2 divided by 24 will give you a 12 that you talked about.
I guess it's the same, but we wrote it a bit differently. I mean, it should equate to the same thing, but I have it differently. But it's kind of the same thing. I have W divided by 24 EI. And then in brackets, I have x to the power of 4 plus 2L x cubed minus L cubed x.
Hussein,
it's kind of the same.
It's exactly the same, actually. I was comparing. It is 100% the same, actually.
It should be fine.
Okay, so I have copied pasted the last week's problem. Now I will say that this is my A. This is my B. And now I will add my A and B. Agreed? So I will say this is my A and V. Let's say the question said that I had to find the deflection at x equal to A. So V at x equal to 2 meter. So it will give me V equal to negative 8.33 into 10 power minus 6 into x power 3 minus 16x square plus 512. V comes out to be minus 7.6 millimeter. Can anyone explain to me the reason of negative? Ghazal, why the answer is coming out to be negative for deflection? Because deflection is like this, right? Below the beam. So that's why your V is coming out to be negative. If someone had put the load like this on this beam and it had deflected like this, then your V's would be positive. Okay. How many students agree? And last but not least, we have students who are saying, why don't you now tackle the portion B? So for the portion B, I will immediately go back and I can, I don't know, hang on for a second. Yeah, you can use this one or hang on. Why did I write V at x by L, x equal to L by 2? This is correct. Anyways. Okay, anyways, so once you solve this problem completely, you can have some expression. So V is equal to minus PB x over 6 EI into L square minus B square minus x square. I suppose this is for the second portion from A to whatever. So this is A equal to 2 meter. I will tell you how did I write this. I will open the textbook. Or you can say that I've copied pasted from my previous problem. L is equal to 8 meter. And my answer will be V equal to minus 187.5. I will open the textbook, Mehmet, into 10 power minus 6 into 28 minus x square at x equal to A. Deflection comes out to be negative 9 millimeter. Why don't you tell me what will be the total deflection of our problem under consideration? It will be what? Minus 7.6 minus 9, right? I think one of the students told me you have to add them. Very nice answer. 16.6 millimeter. Now we have students of our class who are getting confused. How did you write all of this? First of all, I went back to the previous slide. I had written two different V's. I will select one of the V's because I think both of the V's, I'm sorry. In the previous slide, I apologize. I'm sorry. You cannot copy this. You know why? No, ek minute. You cannot copy this. You know why? Because this question I solved was for L by 4 and 3 L by 4. And this question that you are solving right now, it is not for L by 4, right? No. 2 divided by 8 is L by 4. So okay, sorry, I was wrong again. So go back. You will have a V1x here. You will have a V2x here. Both the equations are true for x equal to L by 4. So you copy any one of them and you can do this problem like this. Now, there are students who are saying, but how did you write all of this in terms of A and B? Because this expression is not written on the previous slide. So how did you do that? Yes, you can ask the question, then I will tell you how did I do it. I actually opened the book. When at the end of the book, there is a chart that is present and the author has himself or herself found the deflections. So I just looked at that chart, got the value of V. I just wrote it here. Yes.
So we add them up, right? Sum them up. In previous slide, we add V1 and V2.
I just added. No.
What? Yeah.
No, V1, V2. No.
How do you get this equation, the equation? I couldn't understand that.
I will explain by opening the book.
Intervals are different, yeah. The first interval, it's from 0 to L divided by 4.
But both of them hold true for L by 4, right? You can find V1 at L by 4 or V2 at L by 4. Either one will give you an answer of minus 9 millimeter. Forget about how I wrote that. I will open the book and show you.
We are looking at the point, which is
L by 4.
the forces
L by 4.
L by 4.
So either way, any question will hold true.
Okay, I get it.
But if I had asked you to give me the deflection at L by 2,
so we need to find.
Then what will you do, Bahadur? If I had told you that in this problem, the 150 kilonewton is acting right at the center, then what will be the change in the problem? For the B portion, you will go back to the previous slide and then you will use V2 because V2 holds true between L by 4 and L. So it also holds true for L by 2. And in that V2 only, I will substitute x equal to L by 2, and I will get the value, probably not minus 9 millimeter, some other value, and then I will add it into the minus 7.6. Is this clear?
You know, so finally we found that.
Hello, Tashin Jan. Yeah.
So for example, yeah,
Let me open the book and it will answer your questions.
my question is like we found the minus 9 millimeter, and also we find minus 7.6.
So I added them together. 9 and 7 is 16, right? 16.6.
Okay.
I just added
So
them.
we find at 115 kilonewton.
Only
that part. Yeah.
the question was find the deflection at x equal to 2 meters. So I said okay.
Okay.
If they had asked me to find the deflection at x equal to 5 meter,
So okay. We need to find.
then I will use the part A, and at x equal to 5 meter, I will find not minus 7.6, I will find something else. And then I will add it, the green portion, but this time I will be using the V2 from the previous. So everything will be different. Yes.
At the end of the question, we
Added them.
we added the M1X and M2X.
No, we did not. I did not add M1 XM.
What is the yellow, which is written yellow?
Minus 16.6.
Yeah.
This and this, I added the deflection, not the moment. You said, did we add the moment? No. So I actually did divided this problem into two chunks. One was a completely unloaded beam with a concentrated load. This one, the B. And the second is a completely unloaded beam that has its own weight. I did them separately. I found the M bracket X separately. So these are two different problems.
It's V1, it's V2, and we all added up.
You know, personally, I don't like this approach. I think it is more work if you start doing in an exam. You take the whole problem as a whole and then do it in one go. So if I ask you, can you find the bending moment diagram or capital M bracket X for this whole thing together? For sure you can do it. I'm sure you cut it into two pieces. Do it. No need to divide it into two pieces. I'm just telling you a method. Okay. Okay, before I take your question, just bear with me. Okay, we will take a break. Okay, everyone. So just to be clear, the question that we were doing, I just opened the Beer-Johnston book. This is the table that is available right at the end of your book. Now you can see that this one, I hope it's clear. Hang on. This one. We have a roller here to the right. We have a pin joint on the left. We have a distributed load acting like this. And if you scroll up a little bit, it says maximum deflection, slope at end, equation of elastic curve. So now if I again zoom out a little bit, you can see that the deflection of the elastic curve, equation of the elastic curve, it says minus W over 24 EI, x power 4 minus 2 L x power 3 plus L power 3x. So I used the Y equation like this, and now I will go back. You can see here I wrote minus W x over 24 EI x power 3 and all of this. So I actually could have copied this from here. By the way, I also took 1x common, but anyways. Now, when I have this equation, I can find the deflection at any particular value of x. I also used one more of this. If you remember, I used this particular case as well. It has a pin joint on the left and a roller on the right. And it also has a load P that is acting from the top, which is acting at location A from the left and location B from the right. The total length is L. Now you can see that for x less than a, I have the deflection equation given as y equal to this one. And for x equal to a, I have the equation of deflection like this. So now what I can do is I can add this y, and then similarly I can use x equal to a in this equation and I can add them together. So now you realize that when I was directly using y equal to pb over 6 EIL x power 3 minus L square minus b square into x, here L square minus b square into x and all of this, how did I directly write this equation? Well, I was directly writing this equation by copying pasting from here. So I will again repeat that this is a table. If you can also have a quick look here so I can proceed. So I was actually using the values from here directly. This is a chart in your book. Beam and loading, elastic curve, maximum deflection, slope at end, equation of the elastic curve. I used two different cases. One case with a distributed load and the beam is not having any other load. And the other case I took was if a concentrated load is acting, A from the left, B from the right. And I wrote the equation of, I took the equation of y and I got my y values.
So, for example, if the force is at the middle, like at 3 meters from the left side.
Not the middle. Middle will be 4 meter anyways. This is 8 meters, so middle will be 4 meter.
Sorry.
Okay.
So the equation for the B will be changed, right? Or it will be not same as the previous question. Right?
I just told you that I am following this chart. There is A, there is B, and somebody has directly given me this y equation of the elastic curve. I took this equation, substituted x equal to A, and I similarly used this case and I added them together.
So in exam?
No, in exam, I highly doubt that I will be giving you this chart. You have to do everything by hand. Now, let us talk about thin walled pressure vessels. So what I have is something like this.
What vessel is?
Vessel?
Yeah.
Pressure vessel?
Yeah. Equation of, for example.
Vessel, how to translate pressure vessel? So even in front of your, what is the name of the hostels? 1, 2, and 3. In front of dorm 1, you have this big white color pressure tank. Pressure tank. So that's a pressure vessel. Vessel is just an English word. Coca-Cola can. Who has the can with us? Anyone who brought can? No, this is a bottle. Someone had a. It's a vessel. Coca-Cola can is an example of thin, walled pressure vessel. Coca-Cola can. If you shake it and you open, boom! It just. So that's actually a pressure vessel. Okay, so we have. Then we have X. Then we have okay, let me pause the recording for a second. I have to. So on this element, I have a stress that is acting along the surface. This is stress 1. There is another stress acting along the surface in this direction, and I will call it as stress 2. Again, you can also make another arrow here if you want. This will be stress 2. So anyone who tells me, what do you remember from 1 and 2? Anyone? What do you remember from 1 and 2? The principal stresses, right? So remember that these are indeed principal stresses. I will call stress 1 as the hoop stress. And I will call stress 2 as the longitudinal stress. Because
over the longitudinal axis.
exactly. One is along the longitudinal axis, and the hoop stress is, so for example, if you have a circular cylinder, you cut it, so the hoop stresses will be on the hoop. If it's not clear to you, let me make the hoop stresses for you. How should I explain? Let me explain the hoop stresses. How should I explain? The hoop stress 1 is the hoop stress, right? Yeah, I think I can explain it to you this way. So the hoop stresses will be, if you cut this whole thing like this, and then you have something like this, and then we have let me just, again, I will pause the recording. Let me make some orange diagrams. So now, if you have a fluid inside this that is pressurized, how will the stress lines be, how will the pressure be acting? So everyone will tell me that the pressure will be acting like this, correct? This is the pressure of a gas or whatever. Then you will have another pressure line like this. Then you will have lots and lots of these that are acting. I am trying my best to keep the pressure arrows like this, nice and beautiful, symmetrical. So the surface is subjected to the arrows like this. And similarly, like this. Hang on with me. I think that's enough. You can make 20 more arrows. I don't care. Now what I will do is I will talk about this surface. So now this surface is subjected to stress, right? Why don't you tell me the name of this stress? Probably Mehmet and Bahadur can help us. This surface is subjected to a stress. What is the name of this stress? That is our that is hoop stress, right? Hoop stress, I suppose. I'm not talking about the orange arrows, because orange arrows are the pressure exerted by the fluid. I'm talking about the stress. So you can make yellow lines if you're still getting confused. This is the hoop stress. Similarly, line here, line here, line here, let's say line here, and then you can make these arrows. Correct? This is your hoop stress. And students were saying, but then what was longitudinal stress? It was like this one. Okay. And then I will make lots and lots of arrows. What is the name of this stress? Anyone? These are longitudinal stress. Longitudinal stress is given by what? Stress one symbol. I'm sorry. Hoop stress is given by the hoop stress is given by stress 1 and longitudinal stress by stress 2. Now let's try to do the summation of forces in a particular direction equal to 0. So I have pressure of the fluid multiplied by pi r square is the area is equal to stress 2 multiplied by the 2 pi r multiplied by t, because it is thin walled, so I don't care about whether it's R1 or R2 right now. And no, I do care actually. So let me call R as the inside radius. R is the inside radius. And T is the, anyone? Wall thickness, correct? I do care actually. But in any case, the thickness is very small. So now I will use a yellow color. What will be your stress 2? It will come out to be P R over 2T. And similarly, now I will talk about stress 1. So I will say that pressure is equal to force per unit area. We know that summation of forces in a particular direction for static equilibrium is 0. So for finding, let's say the other stresses, my strategy will be something like this. So I will do, bear with me, like this. Let me make another like this. And now I will say that the pressure is exerted like this. So it will be one arrow in this direction. One arrow will be in this direction. And this is, by the way, nice. These arrows are of the same length. This is just bad drawing. And I will draw it one last time. Let me pause the recording. So resume the recording. Now that I have shown this one like this, I will say summation of forces equal to 0. So pressure multiplied by 2R multiplied by delta X. What exactly is delta X? Delta X is along this line, small little differential element. So let's say this is your axis line. And this is my X direction. This is equal to stress 1 into 2T multiplied by delta X. So stress 1 comes out to be P R over T. Okay, so my hoop stress comes out to be P R over T. And I will just write that the pressure I'm talking about is, why don't you answer this, Usman? The pressure I'm talking about will be absolute or gauge? Probably Usman can answer this. Pressure I am talking about is absolute or gauge? Usman Bahadur, no? The pressure will be gauge pressure. And what is the gauge pressure? Gauge pressure is above ATM, right? Above the atmospheric pressure. We talk about as gauge pressure. So in your car tires, when you ask someone to fill in 28 pound per square inch. That is a gauge pressure. That 28 pound per square inch that you ask the person to fill in the tires, that is 28 pound per square inch with respect to the atmospheric pressure. So that means it is actually 28 pound per square inch plus 14.7 that is already in the atmosphere. This is the concept of a gauge pressure. In all of these equations that I'm talking about, the pressure of the gas or fluid or whatever that is inside this vessel, that pressure will be gauge pressure with respect to the atmospheric pressure. We are not substituting absolute pressures here. So just to put the derivation into perspective, what did I do? I said in order to find the hoop stress, and what exactly is a hoop stress? These are longitudinal stresses. Hoop stress means the stress that is acting in this direction. So I took a chunk, I saw the side view, the pressure is acting like this. Then what I did is, again, this is complete circle and these lines are equal, by the way. I said pressure multiplied by 2R multiplied by delta X is equal to stress 1 that I want to find, the hoop stress, multiplied by 2T, that is thickness multiplied by 2 multiplied by delta X. And then I got the beautiful formula stress 1 equal to PR over T. So let me just do a question. Stress 1 is equal to PR over T. And stress 2 is PR over 2T. What is stress 1? Anyone? It is the hoop stress, right? Okay. And what is stress 2? Longitudinal. Okay. What is T? Thickness of the vessel. What is R? It is the inside radius. Now, just to be clear, this last slide, till now, we are talking about cylindrical pressure vessels. Hang on with me. Right now, we are talking about. So let me talk about the fact that we are talking about cylindrical pressure vessels. So this is your Coca-Cola can, like this. But in general, what happens is that most cylindrical pressure vessels have a spherical covering over it, okay? Half spherical covering like this. And we will say that this is what is known as a spherical pressure vessel. In a spherical pressure vessel, let me make a little chunk. So this is in a spherical pressure vessel. If you have spherical pressure vessel, then you have stress 1 is equal to stress 2 is equal to PR over 2T. And this is for cylindrical pressure vessel. It was pretty boring. I know the derivations, but now you can focus. Stress 1 is the hoop stress. Stress 2 is the longitudinal stress. These are for cylindrical pressure vessels, like a Coca-Cola, like a Coca-Cola can. If you have a spherical pressure vessel, Google images. Do it right now. Do Google images. Look at a spherical pressure vessel for me quickly. Do the Google spherical pressure vessel for me. Look at the images. I would have shown you on paint if I had this. Show me. Show spherical pressure vessel. Okay, look at the cylindrical pressure vessel now. Google it quickly. Got it? Okay. And just to be clear, one last comment that I will make is these are thin pressure vessels that I'm talking about. And for a spherical pressure vessel, we have students who are getting confused. So I will make a cut here. Thin spherical pressure vessel. This is a thin spherical pressure vessel. And you can see I will make, these are the nice and beautiful stress lines. And you have pressure of the fluid inside it is acting like this. Okay, now remember these are principal stresses. And before you go, why don't you do a problem? Is this clear or not? Now, am I talking about a thick pressure vessel or thin pressure vessel? Thick or thin right now? Anyone? Thin, like a Coca-Cola can, okay? If you have a thick pressure vessel, then the analysis is not as easy as this one, because then the stress will vary along the thickness as well. So let me make a very easy. Okay, so again, let me make a. The question says that a pressure P equal to 180 pound per square inch gauge. That is gauge pressure. Anyone who can tell me what is a gauge pressure? Pressure that is measured relative to atmosphere. Is it clear or not? You have heard about it, right?
Yeah.
Okay. I'm not sure whether you have. So this is 8 feet. The thickness of this is 3 by 8 inches. This is a steel cylinder. The question says that this thickness of the spherical portion, it's very hard for me to show you that this is spherical, but I think you get the point. Thickness of this portion, the spherical, because there is a spherical cap like that one. Okay. Is it clear? Okay, like this. This thickness is 5/16 inches. Again, it is made of steel. The question says that what is the question? What is the question? Question says that the outer diameter is 30 inches in this problem. And you have to first find the radius of the tank and the radius of the end cap. So give me the radius of the tank. Radius of the tank will be, cylindrical tank will be 15 inches minus, what is the thickness? 3 by 8, right? Anyone? Similarly, the radius of the end cap will be 15 minus 5 by 6 inches. Is it clear to Usman?
Yeah.
Okay. Now, there are students who are saying that you told us everything, but you did not tell us what is the meaning of a thin pressure vessel. The thin pressure vessel criteria is that your R over T has to be greater than 10. If your R over T doesn't come out to be greater than 10, then that means that you have a thick pressure vessel. So the first thing I want all of you to do is tell me whether this is a thin pressure vessel or not. So you will do R over T? Tell me the answer. Well, 15 minus 3 by 8 divided by 3 by 8. What is the answer? It will be thickness is 3 by 8, by the way. So T, thickness of tank. Is it greater than 10? Yes. Okay, good. Then radius of the end cap divided by thickness of end cap. Can you do it for me? Is it coming out to be greater than 10? Yes, it is. So again, both of them qualify as thin pressure vessels, both the cylindrical portion as well as the spherical. Last but not least, why don't you tell me what is the principal stresses? So I will say tank body, and then I will write end spherical cap. So for tank body, give me stress 1 is equal to PR over T. I'm coming to your desk. We still have 5 minutes. I have plenty of time to check it. And PR over 2T. And for end cap spherical, we have formulas of stress 1 equal to stress 2 equal to PR over 2T. Give me the values. Give me the values. Mehmet, give me the values. You have 6-7 minutes.
Time stops.
Huh?
Time stops.
Yeah.
And time stop. Did you calculate?
So do it.
So what did you do that and in 8 minutes? You came here to calculate that. It's just something. Not to that's almost just keep.
I know you are getting close for me. Give me the answer.
Yeah, no, but it's almost break time.
Huh? See, we still have 3 minutes. It's just calculating.
Feeling happy now? Of course they are.
Okay, gentlemen, I'm doing it myself now. Okay, hang on. I will do it myself. So it is good. Not kilopascal.
Still, standing.
180
Take your pen and write calculate.
into. Okay, what is the R? 14.625, right? Can you double check? Divided by 3 by 8. So the answer is 7020. What is the units? Pound per square inch. This is English system. You should not say pascals. PR over 2T. Can you tell me the answer? PR over 2T. It will be 3510 pound per square inch. Similarly, stress 1 equal to stress 2 equal to PR over 2T, but this time it's an end cap. So I will use entirely different color. P is 180, R is 14.688, because the thickness of the spherical tank and the thickness of the cylindrical tank are different, right? That's why R and T's are different. 2 into 5 by 16. So the answer is 4230, right? So I get stress 1 equal to stress 2 equal to 4230 pound per square inch. Is it clear? And let me just double check. Did I tell you that when I wrote here, I usually tell this to students that remember that in a cylindrical tank, your stress 2 is equal to stress 1/2 for a cylindrical tank. Cylindrical tank, thin pressure vessel, okay? Remember this. Yes, please.
Could you open the previous, the last slide?
Let Usman take a picture. Oh, you can take a picture again. I removed the pictures. Okay. Yes.
In end cap equation, we use P, which is pressure gauge.
Gauge pressure.
Gauge pressure. And we use R, which R we use?
So
R
we have
end
two
cap.
R's. We have R for the thin cylindrical pressure vessel, and we have R for thin spherical pressure vessel, which is the end cap.
So we
Because
use
the
inner
thickness-
radius, right?
because the thickness of both of them are different. They are made up of different thicknesses of steel. But at the end of the day, the outer dia will be the same, right? Because if you have a complete cylindrical tank, the outer dia for the cylindrical portion and the outer dia for the spherical portion is the same, right? Are you getting my point? But the R value will be different, right? Why? Because R is the inner radius, inside radius. So I found the inside radius for both of them. The R tank, the inside radius of the cylindrical tank. Then I also found the inside radius of the end cap. This is the cylindrical tank. This is the end cap.
And also thickness would be 5 divided by 6, right?
So thickness is 5 divided by 6. It is not 16. It is
I was
5
gonna
by.
ask that, Hojam, actually, yeah. I was gonna
Yeah,
ask why you
I-
wrote 5/16.
I apologize. I apologize. It's 5 by 6. I'm sorry.
It's gonna be 2,115 PSI, Hojam.
Oh, hang on. Then I think I have to change
Change it.
everything. Hang on, everyone. I think I apologize. There is a mistake in my question. This is 5 by 16. This is 5 by 16.
Oh, and also the,
Then I think the rest of the question is same.
notion for the R, it will be R.
Okay, then this is 15 minus 5 by 16. I'm sorry. So it was just a little mistake in the given quantity. 5 by 16 here, 3 by 8 here.
Hocam, and also, the rest of this, okay, hocam.
Hussein, it is clear now, right?
Yes, Hojam, yes. No
It
worries.
was just a typo from me all along. 5 by 16.
No worries, Hojam.
Thank you.
I get it now.
Bye bye.
Hocam, thank you for today. Goodbye.
Bye bye. Bye bye everyone.
Thank you, Hojam. See you. Take care.
See you. Take care.
Hocam,
Yes.
The explanation part.
Yes.
Bigger tank and the hoop pressure and.
So
stress and-
let us talk about,
No, hocam, the previous one.
yeah.
And also, that one. Hocam,
See you, hocam.
draw a diagram like this.
Hmm.
So I couldn't understand.
So for
what is
example,
indicating.
I will tell you. Look. What happens is that we have two stresses.
Mhm.
One is the hoop stress
Mhm.
and one is the longitudinal stress. So when I talk about my hoop stress, if you look from, if this is the Coke
Mhm.
can, then radial direction stresses will be my hoop stress. You can see here,
Mhm.
I am looking from the side view, and hoop stresses means the stresses in the radial direction, right? And when we talk about, in fact, yeah, kind of radial. Anyways, and then when we talk about our longitudinal stress, the longitudinal stress is in the axial direction.
Mhm.
So we talked about that the hoop stress, as the name sounds like,
Mhm.
along the hoop or whatever, the stress one comes out to be PR over T, whereas longitudinal stresses are actually less than the hoop stress. They are PR over 2T.
Okay.
We can actually look at from here just to double check whether there is any
Also,
mistake.
hocam, why are we using gauge pressure? Why don't we use the absolute pressure? Like
Huh? No. We don't use absolute pressure because it doesn't make any sense. For example, if you have a pressurized Coca-Cola can,
Mhm.
the outside environment has a certain pressure to it,
Mhm.
right? Now, the pressure that is exhibited on the walls is the absolute pressure of the
Yes.
of the gas inside it
gas.
minus there is an outside atmospheric pressure anyways. So right now, in fact, let me this portion can be put in recording. Oh, it is already being recorded. So the point is that if I have this cylinder that is subjected to outside environmental atmospheric pressure, nowhere in the calculations did I talk about outside arrows that are putting a pressure. Why? Because I already took the gauge pressure. When I take the gauge pressure of the fluid that is inside, that means that absolute inside pressure minus the environmental pressure outside. So that gives me the net value of the
Net value of the
stresses, or of the stresses
acting on the
on the
walls.
object
Yeah.
because of the fluid that is inside.
Yeah, absolutely.
No?
Okay.
You
I
got
got it
it?
right
You
now,
got
yeah.
it?
Yeah. Thank you so much,
Yeah,
Eugene.
no worries.
Thanks so much
Perfect.
for
Thank
today,
you.
Eugene. See you later.
Thank you. Just one thing. I think let's not use the value, use the word radial stresses for hoop stress. I think I was wrong, because if you see, when I make this cut, you see on this wall, I have these yellow arrows. So these yellow arrows are like in this direction. So I don't think we can use the word radial. So longitudinal is along the axis, and these yellow lines are 90° to it.
So it
So
will be
this is the-
tangential, right?
No, don't use the word tangential. It's just hoop stress. Just imagine like this. This is a Coca-Cola can. Use a knife, make a cut right through the center. Now its wall is exposed. This wall has these yellow lines that are coming out because the pressure is being applied in this direction. So these yellow lines are our hoop stress, whereas the longitudinal stresses are along the axis of the cylinder. That is 90° to these hoop stresses. So hoop and longitudinal are 90° to each other. And another thing that you remember is that shear stresses on the exact plane will be zero. That's why we have started to call them as principal stresses as well. Okay, thank you.
Thanks so much. Eugene.
Bye.
Have a nice day.